So what I am going to talk about is natural language processing. That's one of the areas that I'm really excited about on how things are going in the last couple of years. Especially, there were a lot of interesting changes that have happened and how they are applicable to my day-to-day work. So I was going to talk to that, and I'm also going to give a little bit of a history on how natural language processing and deep learning and NLP came where it is, because when I'm learning, like giving a little bit of an historic perspective kind of helps me understand what I can do with it. So I was going to do that. Wanted to get a sense of one of the things that I'm asking Jeff is like, well, is the interest in the group generally to go more technical about like algorithms and whatnot, or more about the application? So wanted to get a sense of what kind of a level of detail would be interesting to this audience. So anybody wants to?
Yeah,
I think both would be great. I think both would be great. Both perspectives would be great.
Okay. All right. Okay. All right. Let's get started, and then we'll see at what level we land up here. So I wanted to start with this story or a blog post. So this came in last year. This was July 2018. Not sure if any of the audience here has come across this yet. NLP's ImageNet movement has arrived. So this was one of the researchers in natural language processing. He works for DeepMind AI now, Sebastian Ruder. He said, natural language processing's ImageNet movement has arrived. So in 2018. And the time is right for practical transfer learning to make inroads into NLP. So this was became quite viral, and there was a lot of talk about this. And I wanted to unpack this a little bit, and wanted to share my perspective of what has happened in natural language processing and what is that ImageNet movement that has arrived or is imminent right now. So I wanted to get into that a little bit. So over the next few slides, I'll go into what does this mean to us and how did NLP progress to this moment. So ImageNet was a challenge that was started by the head of Google at that time in 2009, where what Google did is they made a lot, 1.2 million train images and 100K test images available to all the audience worldwide. And the images were of 1,000 different categories. So there are these container ships and scooter and leopard, like these, there were like 1,000 different categories that the images were tagged for. And this evolved into a large-scale challenge of image recognition. So this was in 2009. So at that time, all these deep learning algorithms, the GPU machines that support these algorithms were not like as evolved or developed as they are right now. And this contest, in a way, transformed or created this race for new algorithms and new ways of doing image, like image-related, like visual deep learning kind of approaches, because that visual deep learning right now is very mature, right? Like you can use a lot of VGG or a lot of visual models that are available off the shelf through big cloud providers, and you can start using it directly for your use cases. So how did that happen? So throughout this challenge, so in 2010, if you see on the right, the error graph was, so the best algorithms were making up close to 30% errors in making this these images. And one of the reasons was, at that time, this end-to-end deep learning, where you just throw in the pixels in there and set up a general enough deep learning architecture and let it figure it out, wasn't the case. At that time, there was still a lot of hand-holding, feature engineering, that kind of work was going on. and the error rates were between 25 and 30, like about 25 till 2011. And then in 2012, AlexNet, one of the deep learning models, picked up, and it brought the error rates within like 15%. And once that happens, and once everybody and then the paper was published on how that was done, then everybody understood the concept, and then very quickly, within 2, 3, 4, 5 years, the image recognition was a solved problem. Like now, the error rate by 2015, very quickly, right? Like within 3 years, got better than human level error rate. So if 3 or 4 humans look at the image and do the tagging, the amount of errors they do, models make less errors than that. So this was quite significant. And then by 2017, the contest stopped because it was kind of a solved problem. So this is what this gave us. So the biggest takeaways for ImageNet for us were, one was this end-to-end deep learning. And if we have a lot of data, like here, one of the things was we had like 1,000 images, right? So 1,000 classes and 1.2 million tagged images. Then we can just throw deep learning based approaches as opposed to manual hand tuning. So that was one. But the second and more significant one was that of transfer learning. And what this transfer learning means to us is that if I build a big model which takes many days on big GPUs, like let's say Google builds something to recognize images, these 1,000 images, that the learning that model has done, to learn any image, first it needs to identify the edges, and then it needs to identify the shapes, and then, oh, this shape is an eye, and this shape is an ear. But all the previous, what is happening in deep learning is the previous layers are kind of learning only edges. And then the next layers are learning kind of to put the edges together to shapes. And the next layers are putting together shapes to faces and things like that as they go on, like these deep learning models. And the interesting thing is the first few layers of this network are completely reusable. So if you just throw away the last layer, because if my business problem is I'm not interested in these 1,000 images. My business problem is let's say an officer is going to an inspection location and see if there is any issues, and I want to find a ladder that is not in the right place or something like that. What I can do is a lot of I don't need 1.2 million tagged examples of photos of what I want. I can reuse a lot of the work that has been gone into this edge detection and all, and only change the last layer. And only with a few examples, like a few thousand examples, now magically I can start making things work that otherwise was impossible to get. So one of the challenges when I was learning this was, I don't know if many husbands get this challenge where my wife tells me to buy a watermelon, and then when I come back, she says, "You didn't pick the right one." I don't know if husbands have felt this pain before. And I was thinking, what if I just take pictures of watermelons and create only the last layer for the pictures of the watermelons, and figure out whether, based on the picture, the model tells me that, yeah, this was good or not. And I just keep giving it training data. So if I recruit, 20 friends, and each one of them gives me 10 to 20 tagged pictures of good watermelon or bad watermelon, earlier, before deep learning, I would run out of money before getting enough images for it to train to do anything useful. But now with this transfer learning, just with a few thousand examples, I can start making something really interesting happen. And the reason only a few thousand examples work, because a lot of learning has happened on 1.2 million trained examples already, and that is able to get transferred. So that was the biggest takeaway from ImageNet. And the assertion here is that NLP's ImageNet moment has arrived, which means that NLP is at a stage where a lot of pre-training trained models are available that we can use with just a few thousand tagged examples of our documents. and we can use them. So far, going good at a good rate, good speed, or too high level?
Yeah, it's really interesting so far.
Yeah,
for sure.
Okay, all right, sounds good. All right, so wanted to come into the NLP and one of the ImageNet equivalent challenge of natural language processing. And this was one of the challenges when I was, this is a very standard SQuAD, they call it a SQuAD database, which is like an ImageNet equivalent of language. So what SQuAD database has, it has like hundreds of thousands of such passages. So this is like a passage about Normans, Robert something, and another Norman adventure previously elevated to the dignity of Count, and he ultimately drove Byzantines. Like there is a big passage, and then there are some questions that are asked on a passage. And what the group who created this have done is they have got Amazon Mechanical Turk who got humans to give answers, and they have each question answered by 3 different human beings, just to make sure that the humans are answering the same thing. And then you just pass this data to the model, and the goal of the model is to come up with the answer based on this passage. And so this is an example. What was the name of the Count of Apulia? And the name was Robert. And then the 3 humans have said the same name, right? And this is the answer. And when did this fall in Normans? And the answer was, some humans gave only the year, some said February, and then this was the model prediction. So the model is like, this is what is happening. So model is reading this passage and somehow getting the right answer based on the question that is passed to it. And so this challenge has been going since 2016. I actually participated in this too when I was doing the Stanford course. And what very interesting thing that has happened, so this is as of yesterday or earlier this week, human level performance, so this is F1 score on 89.45, and the human level performance is slightly low because 3 humans look at the same question and give slightly different answers, so that performance is not 100%. But the model performance with BERT, which is one of the model that has come up last year, based on which that post was written, actually beats the human performance on. So this is kind of like this question answering, which you can think of as the blocking problem, like ImageNet equivalent of NLP. That this is one of the problems. Looks like kind of is getting solved here. And when I was doing this course, this was I think last year with Stanford, we had 2 leaderboards. One was a leaderboard where if you were using a pre-trained model, and one was if you wanted to invent your own approach without doing the pre-trained model. And this difference was significant. So the leaderboard where we were not using any of these pre-trained models were giving like the best of the best were like 70s. That were the ones that were getting. And the leaderboards where we were using BERT, we were not getting as good as these guys at whoever these top researchers are, but we were getting like 83, 84 quite easily with just using this basic BERT model. So there was like a 70 to 83, 84 just because of all the pre-training that has happened. And that pre-training was done by the people who created BERT. BERT was also created by some folks at Google, where they looked at all of Wikipedia and the model just learned to predict the next word. So they call it the language modeling task. And once the model is built to do that, then you can just ask the model to do some other task and it starts doing significantly better. So that is something that has changed or happened in the last, this is very recent. This has been not even a year since this latest BERT model that has come out. So this is kind of an exciting time for NLP for me. So far, so good?
For sure.
Yeah, I'm usually used to speaking to the crowd, so I get to see the responses and all here. Like I'm looking at the computer and speaking, so I keep asking the question. Sorry, but I'll keep moving till if anybody has any questions, then please stop me and ask. So motivation. So this ImageNet movement has come. So I wanted to go back and come step by step to what has led. What are the significant steps that have happened that has led to this state of NLP? And at each significant step, what breakthrough had happened, and what all things can we do with it? Like, what are the business applications that we can do with it? So I don't know if you had seen this 80% figure before, but this has been presented by Gartner and some other sources too, where by talking about unstructured data. So while big data technologies and techniques are unlocking secrets previously hidden in enterprise data, the largest source of potential insight remains largely untapped. Unstructured data content represents as much as 80% of organizations' total information asset. And I don't know, like what I have seen here, or even in the previous cases, this was very true, where there were a lot of very mature data warehousing kind of practices right from the 90s, right? Like people got data stage and Informaticas of the world and slicing and dicing the data and doing all sorts of BI and reporting. But that was primarily for the data in the tables, where there were numbers and there were categories, like drop-down lists, right? Not so much with text data until very recently, until like 3, 4, 5 years. At least I haven't come across a lot of insights like gained from text data, far from the levels that we have seen done with the data warehouse or other structured data. So a lot of problems I've seen, like even with these machine learning and deep learning tools, like with the structured data, you still get a little bit of a lift over the problems, like maybe like quite reasonable amount of lift using deep like machine learning approaches. But a lot of that work has been done in many of the big organizations just because of the data warehouses and so many BI teams looking at the same data over and over again. But this text, and by text I mean like documents. So for example, forms, intake forms and documents have form text on what was the injury, for example, in an insurance context, or what happened, like what was the incident that happened, or notes from a case manager, like so many types of documents haven't really been used to do the same level of slicing and dicing that structured data has been. So that's the motivation. So can I use all these BERT and ImageNet movement of NLP and all to do something like that? So that's my motivation in the future slides going forward. So we'll start with bag of words. I'm thinking many of you might have used this kind of an approach, and this is like the first approach in pre-2013 was quite prevalent. So this is like, I love this movie, it's sweet, but with satirical humor, the dialogues are great, and you read this movie review, and this can be a movie review, or this can be somebody writing the review of the performance of your company, for example, right? And what you do is you take all the words and see how many times the words have come. And then you create a vector of this. And then you pass this vector through some standard models like linear models or SVMs or things like that. And then this tells you what is, like in this case, we are trying to predict a sentiment of this text. Like, is this person happy or not? Like, let's say this was a tweet and somebody had created a tweet on my company or some insurance company or somewhere. I wanted to, in an automated way, find out whether it was positive or negative. You can quite easily do that with this kind of an approach. So this is bag of words representation. So you call it bag of words or TF-IDF, right? Like if you have heard of TF-IDF stands for term frequency, which means great comes 2 times. So that's the term frequency times inverse document frequency, which means that there are some words like it and to and but and the. They're just so common across each document that we want to value them relatively little as compared to some documents like whimsical, like some words like whimsical, which kind of comes rarely. So give more importance to rare words. So that's called inverse document frequency. So this term frequency times inverse document frequency is used, like even Google started, even for search, use, like that was like the basic building block, right? So this has been around since 2013. And this gives quite strong, surprisingly strong baselines for like document classification. Like if your classification especially is with some very strong words, like so there is an input which describes an injury and you have to tag the type of injury, then there are some strong words about the body parts or the medication or the type of injury, which very quickly the algorithms somehow pick up these trends very well, especially the S3M related models, and give a very strong baseline for document classification. Spam filtering has used these kind of approaches for a lot of time, and some basic intent detection and in bots use this for a long time, and information retrieval like Google style search has been using this for a while. But this representation of each word and its frequency is limited because there might be some words that kind of mean the same thing. So you have the number of words here increases a lot, right? So you have the total number of like the length of your vector is the length of your vocabulary. So the words in English. So let's say you want to consider 60,000 unique tokens in English, then the length of the vector is 60,000, where many of the numbers are zero. So this gives a lot of sparse vectors, which has a lot of problems in an algorithm. But still, this gives a very strong baseline. So pre-2013, this was a common approach, and I still use it to get quick baselines for a lot of my classification models. So the next step, and I use this a lot, happened on how can we have each document or each word represented better. And one of the ideas that got very popular was this "You shall know a word by the company it keeps." So this one was in 1957 by J.R. Fork. And what the algorithm that used this was, let's just take untagged data. So you take a lot of Wikipedia and just find out a word based on the co-occurrence of that word in the context of other words. So if you find the word toad and you find the word forest in the same context, then the word toad and forest should be kind of related. So what if we have each word represented by a standard like length vocabulary, let's say 300. So each word is represented as a vector of 300, such that the words that are similar, the two vectors are also similar. So dot product of the two vectors are similar. And the algorithm that was used was, you try to predict, like if you have 5 words, you try to predict the middle words given the 4 words on the side. And if you do this on an unsupervised data, enough unsupervised data, then it starts giving you word vectors which start being very meaningful. And this was quite magical result that started happening. So this was initially done in 2003 by Thomas Mikolau, 2013, sorry, by Thomas Mikolau at Google. And what happened is, below, if you see the vector for man and the vector for woman, I don't know if you've seen this. This man, woman, king, queen became very popular in the last couple of years. But if you haven't, then what happens is, now we have a vector for each word. So we are not representing each word as just a 0 or 1 like we did earlier, but as a dense vector, such that the vector for man and the vector for woman are the same direction as the king and queen. So if you take the vector for man, and if you subtract the vector for woman in there, and if you add the vector for queen, the nearest vector you will see is the word queen. So now you can do almost like math with words. So now you've brought the words to this place where your algorithms can kind of do better. Like at a simplest approximation, if you have a sentence where you say the person got injured, you can add the 3 vectors together, and that's your basic approximation for a sentence, for example. So you can start doing very interesting things. And when they ran it on enough data, they saw some other characteristics, like Spain and Madrid, Italy and Rome had kind of the same distance. So you the words kind of learn the capitals on their own. And there are many such examples. If you look up word2vec, you will see a lot of very interesting examples that you'll see. And it also was kind of getting the verbs and tense, so walking and walk. So if you take walk and walking, so walk minus walking plus swam, and the nearest vector you'll get is swimming. So you're representing words in a very mathematical way now. So what did this do, and how does this help? Well, so if you run word2vec, word2vec is freely available. This algorithm word2vec to find the nearest word, like based on the nearest word, find a vector for the word, is open source, freely available. You can run it quite quickly, even without GPUs on like a regular machine. It will take a couple of hours if you give it like enough corpus of like hundreds of thousands of nodes or something like that. And then just for fun, if you do some experiments and say, find the nearest word to appointment, just based on going through so many documents, what other, like based on the context of the word appointment you've seen, what other words come in the same context? And magically it starts giving acronyms or spelling mistakes, APPT, APPTAs, appointments, or words that are similar: visit, appointment, visit, booked, scheduled, advice, told, said, right? Like shift, day, night. Magically now, just on your own data, running this algorithm, it represents words based on how it is in your corpus. Tylenol, for example, like Tylenol is same as ibuprofen, Advil. It somehow figured it out on its own. When you do this, it's quite a lot of fun. It's quite magical. And anti-inflammatories, tramadol, painkillers, like it kind of figures that out on its own. Even like January, this was interesting to me. Jan, right? And it found the months that are kind of closest. Feb and December were closest to it. So it found those, November, October. It found most of the months, but not May. Any guesses why?
Because it's a word with other meaning?
Yeah, exactly. So it got confused. So this algorithm has that weakness, right? Like, so I may have gone there. So that word is used in another context. So somehow this algorithm, missed that. So there are some disadvantages to it, but still it gives something really interesting, right? Like, so you can do, like, this is a good starting point for now. You can, if you had a long vector of just zeros and ones for each word, you cannot do too much of deep learning with it. But now, once the vectors, words are represented by these dense vectors with something like this, you can do all these deep learning approaches with it. So this is something that we started doing about 2 or so years ago with word vectors, started using word vectors. And what word vectors do, and this is kind of generally true, is overall, like, take whatever algorithms you're earlier using for classification and all, and it gives a boost of 2 to 3% points on accuracy for your previous approaches. It starts making them slightly better. But you can do other things too. So for example, if you find the word stress and you find, give me the closest words to stress, and you'll find some very interesting words. And then you can use these, like if you have human-generated keywords for, let's say, social media monitoring, or let's say you are triaging your workload based on like, oh, so the head injury, send it to this department. And for that, for the head injury, you'll come up with like head, injury, and like different words to have head, but you cannot come up with all the words. But now if you have run word2vec, it will give you the words that are related to that word. So it can kind of do a better job at catching more social media mentions or doing a better job at triaging. So that's kind of a net new application that comes out of this.
So yeah, so there's one quick question. Would you mind commenting on inverse document frequency weighting, IDF or TF-IDF?
Yeah. So what about that?
They just said, would you mind commenting on it?
Oh, sure. Should I comment on IDF weighting?
Yeah, I think they were just interested in what IDF is.
Okay, sure. Yeah. So IDF is, so this was IDF was an IDF is kind of a strong idea, but in the world before these word vectors and everything. So on when you had these words like great, love, recommend, if you have each word, like if you're creating an algorithm that takes each word and then how many times it comes, then words like to and the and but and I kind of dominate a lot of these documents because they are true and like they come in all these documents. And we want their value to be kind of suppressed so that really the words that are differentiating words that help me with the classification are kind of enhanced and the others are suppressed. So one idea which kind of does this smoothly without having to manually go through each of the words is just take your whole corpus, take all the words and come up with the frequency of that. So if the frequency of the word the is very high, 100,000, then give the weightage to that word inversely proportional to that frequency. So the most common words will be the least useful. But the most unique words, like some of the words might be like a medication or like a specific or whimsical or something like this. This will have the lowest frequency in your whole corpus and they'll get the most weightage. So of course there are some limits where the spelling mistakes that only happen once, we don't want it to get a weightage, so you have some cutoff. But that's the idea, and that was the basic idea that was used at Google when they were creating their search engine. So what they did is if you're trying to find something, I want to find music related to something, and then they keep like all the different websites that you can potentially go to. They see the terms that you use in the search and their inverse document frequency. So I want to find the music. They don't use the word the that much, but like whichever, like if you have the specific genre of music, like Indian classical music, then Indian classical document frequency is low. So they focus more on those words kind of thing. So yeah, maybe that's the comment. But yeah, so that was all before this word, the magic of Word2Vec, and us getting interesting representations of words where we can now use them directly into algorithms. Okay, so this is Word2Vec, and immediately boosts the accuracy. So you can take your standard classification tasks and get the accuracy better, or use it to augment human-generated words. But still, the problem is we are still at the word level. We are not at a sentence level, right? Like you can argue that words by itself, like we earlier saw an example of May, it may be versus the month of May, or the bank. By bank, do I mean a river bank, or do I mean the bank where I do business, or I bank on something, like different things. So the words together in the sentence context are needed to do more refined, more valuable things. And sure enough, so this is a sentence understanding. So this was one of the models where like London is the capital and most populous city. So if you give this as a sentence, then you can, like as a human, we understand, right? Like we are talking about London and it is a capital. So this is the subject, is the verb, and its populace is a modifier. Like we kind of know what is going on just naturally, right? Intuitively. So there are ways using deep learning to get these dependency parsing, that's what they call it, where you know the words in the context of this sentence. And the top dependency parser, again, was come up with Google, and they have open sourced it. They call it something funny, Parseface or something like that, but they made it available in 2016 for anybody to use. And you don't need to go and use the parser. If you use standard natural language processing libraries, like one of my favorites is Spacey.io, then they have it built in. You just give Spacey and give it a sentence, and it will give you which one is the verb, which one is the subject, and it will also give you what depends on which. And then you can do some interesting things. And I had an example of an interesting, it looks like there is another question that comes in.
I was just sharing.
Spacey.io. Okay, oh, you just shared it. Okay, sounds good. Yeah. So this is a really powerful library that I use for deep learning. Anyway, so now we started going beyond just words, but also into sentences and sentences parsing. And from 2013 word vectors, now we are in 2016, where even this sentence parsing is a kind of a solved problem. It does it 94% accuracy with standard English sentences. So this is also a solved problem. So what can this do? Well, this can convert, and this was a very important idea for me. This helps to convert text into structured data. So not like just doing classification, look at the whole document and classify. But let's say I want to, like, there is an input form and the person came in and they came in on this date. So I want to find date of injury, or I want to find the date when the person went back to work, or date when they first came to a hospital, things like that. Just looking at the text, I don't want to just tag it as, oh, this is this type of injury. That's at a very high level, but I want to do something at a more subtler level, where I want to look at each sentence and then come up with the tagged structured data for it. So some of there are names for this, right? Like, so one is named entity recognition. So if you find a named entity, like Apple stocks are going high. So if there is a named entity which is Apple the company, and you want to look at a bunch of tweets or a bunch of news articles and find this named entity Apple, and find the context or find the sentiment specific to this named entity, and you can start doing things like that. Or semantic role labeling. So what is the role that this word is playing within that context of a sentence? Or constituency parsing, again, finding different constituents within the sentence. Or advanced sentiment analysis. So within like sarcasm, or within a movie review, sometimes they say this movie was really good, but this happened. So there are like a lot of advanced where, or you want to find within a given overall, if the news report is positive, but the sentiment about the specific types of stock is negative, you can do things like that. And I wanted to show an example of what, and this is a script that I had written in Spacey, and I had to change the text that I gave in just because the data that I use, I cannot, I need to be careful about, but I made up this statement. So, Mr. Imaginary Patient, so this can be a typical note that comes in like a doctor's office, or in a hospital setting, or in an insurance setting, right? Like, so Mr. Girish, or Mr. Imaginary Patient injured his leg on this date. He missed work on this date. He returned to work on this date. He was admitted this date. He has not been back to work since this date, as per the doctor's advice, right? Like, so I have this. Now I want to convert this into something structured. Once I pass this to Spacey, Spacey gives me this dependency parsing. So the imaginary patient, this is a modifier of this. This is the injured is the verb. He is, like, it will, like, this is like, you can right now go to within Spacey, there is I'll send you a link where this is like an open source service. You can type in any sentence and hit enter, and it will give you a parse tree for that sentence on the spacey.io website. But what you can do is, now you can use these tags and these arrows and what points to what to do something like this, what I have done below. The subject, verb, object. Imaginary patient is a subject, got injured on this leg on this date. Now I can start, okay, so this is my injury date, right? Like, I got the injury date, and then what was injured leg. So I can start making structured data out of this. Or he missed work. What was the first shift missed? His date, right? Like, now I can take this text and start putting structured data into this. Return date. This is the return date that came in. And then the last one is, there is a negation to the last statement, right? He has been back. He has not been back to work. So it also captured the negation here. So not. So this is hasn't been back to work. So you can use this to extract, like, this is more granular level of what you can do with your documents. And I feel this is much more relevant and has many more use cases than a standard, like, take this big blob of text and identify it as which category, or as positive or negative. Like, I found this much more useful. Was there I heard a ping. Let's see if there's a question. William Faulkner's sentence in the parser. Sure, yeah, I'll send the link to the parser. Okay, where is my? Okay, so this is about the sentence understanding. So now you're kind of parsing the sentence and getting the sentence understanding. Now the next step after this is taking the sentence and representing the whole sequence, like within the sentence, as the meaning of the sentence. So here it's still this is doing more discriminative, like what is each part, right? It's still not a meaning representation of the whole sentence. So now what if I want to do a meaningful representation of the whole sentence? So, and this was an example you'll see in a lot of research papers here. The man reached the bank after crossing the dash. What could the last word be? So,
street.
Yeah, crossing the road, street, or reach the bank after crossing the river, right? So the meaning of the word bank depends on whether there is a road or street, or whether there is a river, right? So so now the meaning here depends on the context here, right? So there were some other examples. He got a trophy, but he couldn't. And he put the trophy in the bag, but it did not fit in because it was large. Now it was large, so what does it mean? So it means that the trophy was large. But if we say because it was small, then that it means that the bag was small. So within the context, depending on the context, the things start meaning different things. And that's why one of the things that is happening with deep learning is in the deep learning model, you can give the whole sentence to the model and then come up with, so I love to eat everything. And so the model is given the whole sentence. And then the output of this is the kind of the meaning of the whole sentence. And this is kind of think of it as your sentence vector. And now you can do potentially even more interesting things with it. And one of the most obvious one that this was used for is translation, right? Like you take the sentence, like if you want to translate the man reached the bank after crossing the something, then you can't just translate one word at a time because this last word will kind of tell what that bank word means in a different language, right? So now we are, and this is called sequence to sequence. So this is becoming quite popular now. And there are many sequence related algorithms. So there is a algorithm from Facebook called InferCent, where it infers the meaning of a sentence. So it takes the whole meaning of a sentence and creates a vector, like we had a vector for words earlier. Now you can have a vector for a sentence. And Google has something similar, which is called Universal Sentence Encoder, USE. And it's a free open source model that you can just take and use, which takes your sentences and gives a fixed length vector. So you can now pass that vector to your algorithm and start doing interesting things. But this particular approach is called sequence to sequence. So the input is a sequence rather than just one word at a time. And output can potentially be either one or a sequence. So in this case, the output is also a sequence where you're giving a translated sentence. And what this helps us do is machine translation. This was one of the popular applications of this kind of thing. But even voice to text, right? Like a phone call comes in and it gets transcribed immediately into text is becoming very much possible. Summarization. So you give the whole document and I want the summary of that document to come out. So that's very common too. Text to SQL is coming up too. A lot of, there are some benchmarks for text to SQL. And then I don't know if you heard about GPT-2, an algorithm that is too dangerous to release the open source code. Like there was a little announcement earlier this year because it can do natural language generation that is so good that it is like human level generation. So I kind of still think there is ways to go in there. But in some specific use cases, yeah, sure, it can be dangerous. And then advanced question answering. So now we are to the point where we started, where I showed that scored question answering. So now with this sequence representations, Now you can do some question answering where you give a passage and you ask a question and you get an answer, so you can start doing that. So those are some of the common ones. But for me, the most important thing, and this is what I do a lot, is end-to-end machine learning with text and structured data all combined together as one. Like I do not, like most of the time, our problems are not that, oh, do this document classification. And then separately, by the way, I also want a risk score for this, right? Like it's all together. So you have, let's say we are in an insurance setting or in a hospital, and we have a record of a patient, and the patient has a lot of structured data like gender and whatnot, and there is a lot of text notes that go with it. I want to use all of this data together, like how a human would do, like how a case manager or a doctor would do, and come up with a prediction. So now with these representations of sentences or big chunks of text, like it can be even a paragraph, I can now combine both the structured and the unstructured data and truly do these end-to-end models. And what we have seen in ImageNet is making these end-to-end models is working out much better than doing these human feature engineering where we are trying to figure out what features to do and all. Just if you just do representations which are good, where text is represented very well, structured data is represented together, and give it enough examples, then the best models are where you can potentially do this end-to-end. And that is becoming more and more possible. And this for me is the biggest use case for, of course, all other use cases to machine translation and all are important, but in corporate settings, I'm thinking this is the end-to-end machine learning is the most powerful or interesting use case to me, at least. There was this paper, and this kind of summarizes this use case for me, at least. Again, from Google, scalable and accurate deep learning with electronic health records. This came in last year. And this proposed a representation of a patient's EHR record with text and all the values of different test results, everything together, and demonstrates that the deep learning methods uses this are able to accurately predict some medical events. So some of the events they did was in-hospital mortality, 30-day unplanned readmission, prolonged length of stay, and the final discharge diagnosis. Like if you want to get all the inputs from text and all the structured data, and then predict things like this, the model that they showed outperformed all the traditional models because it was end-to-end and the power of end-to-end. It was able to outperform all the traditional models. So this for me was a quite encouraging paper, which kind of summarizes what I'm the most excited about in this end-to-end machine learning. So yeah, coming back to the NLP movement, so GLUE is another benchmark. So GLUE has like that question answering that I showed you. That's one of the challenges. GLUE has 9 such challenges. So some other are like finding paraphrases or finding entailment of a sentence. So if you have a sentence 1, and then there is another sentence like, I had a roommate and we got together very well. And the next is, and the next week we went for a movie together or something like that. So that's an entailment. So there are 6 or 7 different language challenges, and all together are called GLUE. And over the years, the GLUE is getting closer and closer to this human performance. So the BERT, the model from last year, is here. The GPT-2 that they haven't released apparently might be slightly better than this, for example. So we are getting very close. And one of the things that is happening is these models are right now such that if you just give it more data, so this was trained on like billions of tokens on Wikipedia. But what they did is they used the same algorithm and they trained it for slightly bigger data for longer time, and it did better. And we haven't reached that threshold yet. As the machines get faster, just using the current models and more pre-trained data, it will just get better without needing any breakthroughs in algorithms or anything like that. So yeah, so that kind of is the summary of like if you start using these pre-trained models for doing some of the things that we are doing, like you even use universal sentence encoders, word models, then you can do something like which was not possible even 1.5 years ago, for example. Wanted to summarize, like, oh, there were some things here, so let me see. What is the counterpart to end-to-end machine learning?
Yeah, you were mentioning end-to-end machine learning. Like I would assume the data collection and the data and the service for the machine learning is all done by like company. What would be the counterpart to that? That somebody else does the data collection, or?
No, not the data collection. It's more from the feature. So, for example, when people were first doing voice to text, they took different pieces of the text, like and they called it phonemes. So they kind of created different phonemes out of voice, and then used that as a representation, as an input to a deep learning model. So there was some feature engineering that was done, and later on, what they said is, listen, forget about us doing all these, figuring out these phonemes and all. Maybe they are thought of by us, right? What if we just give the raw audio to the deep learning model and just expect it to get us an outcome at the end of the day? And they found that the more end-to-end you do and the less hand-holding and feature engineering you do in the middle, you start getting like better results. So in our case, for example, one way to not do end-to-end deep learning is use all your structured data. Let's say you're predicting, like you're having a customer record and you want to find whether this person will relapse or come back to the hospital in 30 days. Then use all the structured data, and from the text data, you decide that, okay, let me do sentiment analysis, and then take one sentiment and use that as a feature. And then say, let me do some other like important words analysis, and then use that and add that as a feature. So you think of different features and add that as features. And this has been done since, even now it is being done, but till 2 years ago, like we kind of thought of different ideas and features, and then we, so that for me is not end-to-end. End-to-end is like, just give the model the text, it figures out the representation and gives out an answer.
Okay, good point. Thanks.
Okay. Okay. So wanted to summarize. Like I spoke while going through this, I spoke about a lot of use cases. So wanted to give an overview of where I see each of the use case and what level of maturity they are at based on my experience. Like we've tried like all these use cases either at a high level or gone deep into making models out of it. So basic chatbots, like things like IT help desk, like I want to order this, I want to change passwords. Very high technology maturity. The best way is like pay-per-use cloud vendors like Azure and Google has the Dialogflow and all these services doing very good. So maturity was very high. Advanced conversational interfaces like are not as good, like based on the POCs that we did, are not as good as you would expect, like or as you would think, like with Siri and everything doing very good, you know. But if you want to have a chatbot that kind of is replacing the person who is taking a phone call, then there are some niche players, but not quite there. So there might be some ways to go in there. Text classification, sentiment analysis, again, a lot of progress with all this BERT and everything is at a very high level. The recommended approach do in open source tools, things like Spacies, open source. You can do a lot with that, but there are some pay-per-use vendors where you just pass API and it gives you the sentiment of a tweet, and it does the structural breakdown and all. Like a lot of cloud vendors do that too. Extract structured data from text. Again, things like Spacies are great, but if you have a specific like biomedical domain, then there are some vendors that do, like Amazon Comprehend Medical is specifically trained on that, and it does quite well on those things. Machine translation and voice to text are completely like products, commoditized. So there is no point in us creating in-house to do this. Like this is a very typical commodity application. Pay-per-use clouds are quite good to do things like that. So I wouldn't do any in-house development for that. Open domain question answering and natural language generation, even though what GPT-2 and all say, not quite there. I think the maturity-wise, it's still ways to go for open domain. specific domain question answering, like IT chatbot or something, it's good, but open domain not. End-to-end models, this is my favorite, and this is a developing area, so I'll still call it medium, but this is in-house development is the best way, using open source deep learning tools like TensorFlow or PyTorch. PyTorch is becoming more of my favorite now. A lot of these models are available. You can get like BERT model and start using that. So yeah, so this is kind of overview of the use cases as I see it, and it's 9:59. So questions?
Jesse here. Have you ever done any document categorization or basically summarization of? I talked to one company in the States that's using a software called it's basically a module called LexRank.
Okay.
Yeah, you feed in the document and it literally spits out a summary, similar to what Google would provide in the description.
I see. Yeah. So document summarization, yeah. So that's pretty good. We have used some in-house models to do some summarization, and they were pretty good too. So there are some, So I see in-house both in summarization. I agree. There are some vendors who are doing very good too. Good point. Any other questions? We're at the top of the hour. If there are any further questions that come to me, please feel free to reach out to me. Like even individually, I'll be happy to share my phone number, and I love to discuss like specific problems and all. I'm open to do those things. So please feel free to reach out to me through email or phone number. I'll share it via Jeff.
That's great. Well, thanks so much, Girish. Honestly, we all took away some great concepts and some new acronyms. All the Sesame characters were all new to me. Bert and Big Bird and Bert. And
I know, yeah. There is Elmo too. Elmo was the model before Bert, so yeah, there's a big thing. Yeah.